fair. Welcome, everybody. You've been watching the wonderful science art communication of the impacts of climate change produced by Environmental Graffiti. That's available, you can see it on the website, by the artist Alice Singer, who allowed us to use this free of charge. Unfortunately, Christy Goldfuss of the White House Council of Environmental Quality in the US is unable to make it to Marrakesh due to changing circumstances. However, I am delighted to welcome Philip Duffy, who is President and Executive Director of the Woods Hole Research Center. He held the role of Senior Policy Advisor in the White House Office of Science and Technology Policy. So Philip, we welcome your words.
Well, thank you so much, and thanks to all of you for coming. I know at this time of the week, especially perhaps this week, the temptation of boisson may be stronger than the attraction of science. So the event tonight deals with the oceans and the cryosphere, and I'll say just a couple of words about each. You know, the oceans play obviously an incredibly important and underappreciated role in climate change. And in the most simple terms, greenhouse warming is the Earth absorbing more energy from space than it emits back out into space. And if you ask where is that excess energy going, over 90% of it, almost all of it, goes into the ocean. Only about 1% goes into the atmosphere. So when we think about global warming, we tend to focus on the atmosphere because that's where we happen to live. But really, climate change is happening much more in the ocean than in the atmosphere. The other important statistic and fact about the ocean's role in climate change is that the ocean absorbs roughly 25% of the carbon dioxide that humans emit into the atmosphere. And as you'll hear tonight, these additions of heat and energy and carbon dioxide into the ocean are having profound consequences. Similarly, the Arctic is what you might characterize as a hotspot of climate change. As you probably all know, the Arctic is warming at least twice as fast as the rest of the planet. This is resulting in changes there that are not just detectable, but actually obvious. And as you'll hear tonight, warming of the Arctic is having consequences, regional consequences that are, again, not just detectable, but actually obvious. It may be true, though, that although the regional consequences are very significant indeed, it may be true that the global consequences of climate change in the Arctic, although they've yet to be felt, are potentially more important. Indeed, I think nowhere is the concept or the immediacy of the concept of thresholds and tipping points more important than it is in the Arctic. And two examples come to mind, again, of thresholds and tipping points in the Arctic. One is greenhouse gas emissions from thawing permafrost, and the other is the commitment to the eventual complete melting of the Greenland ice sheet. And in my opinion, it's tipping points like these in the Arctic and elsewhere that really drive or should drive the urgency behind addressing global climate change generally. We can't wait, and as you'll hear tonight, the commitments that collectively the world has made so far are not enough, are nowhere near enough to prevent the most serious consequences. So more ambition is needed, and more ambition is needed sooner rather than later. So we have 5 distinguished speakers tonight. Carol Turley of the Plymouth Marine Laboratory will introduce them and will moderate the following discussion. Thank you.
Thank you. So I get to introduce myself. Thank you. Thank you. It was that name's Carol Turley. I'm from Plymouth Marine Laboratory. I was the Knowledge Exchange Coordinator for the UK-wide Ocean Acidification Research Programme. Currently hold a Senior NERC Knowledge Exchange Fellowship, and I've been involved in a number of ocean acidification research programs in the UK and the EU. And I have advised a number of policymakers in the UK and the EU and even the US. Still willing to, by the way. So, good, thank you. So just back to basics. We've all aware that carbon dioxide concentrations are increasing in the atmosphere, and they're rising year on year. And this year was a year when it went above 400 parts per million. And it looks like most of the year will be above that. It all depends what happens in the next 2 months. So we've crossed a threshold already. Now, the increasing carbon dioxide in the atmosphere is due to burning of fossil fuels and, to a smaller extent, deforestation. But only 47% of the emissions remain in the atmosphere. The rest is taken up in equal parts by the biosphere, the land plants, and the ocean. And what I'm focusing is what happens when that carbon dioxide enters the ocean. So 25% enters the ocean, and that, whilst reducing atmospheric warming, causes ocean acidification, because CO2, when mixed with water, produces an acid, carbonic acid. And this is what we term ocean acidification. And it's a change in the pH of the ocean, which is a measure of the acidity. Ocean acidification is happening now and is measurable, and it directly reflects the atmospheric CO2. And you can see how the CO2 emissions increase year on year, and the pH of the ocean decreases. But there are other major changes to the ocean carbon cycle as well. It's not all about pH and hydrogen ions. It's about the decrease in carbonate ions and increase in the bicarbonate ions. So there's an awful lot happening, an awful lot of changes happening to the carbonate cycle. And these have varied impacts on marine organisms. This is aragonite saturation. It's global model projections of aragonite saturation. Aragonite is a calcium carbonate mineral that for some structures, coral reef structures, and some skeletons and shells of animals. And you can see that at the very beginning, the whole ocean is well saturated. What you want to see is the white bit is the white color is one, which essentially divides saturated from undersaturated waters. And you can see very early on that the polar oceans become undersaturated with respect to aragonite, but it's a global ocean phenomenon. With the supersaturation that's happening in the tropical areas, like you can see there in the dark blue, is rapidly decreasing too. So this is something that's of great concern. And when it becomes undersaturated, unprotected shells will dissolve. And we can actually see this in seeps, carbon dioxide seeps through coral reefs of Papua New Guinea. And you can see a progression from here, from away from the reef fence, moving right into the carbon dioxide, where the carbon dioxide is going through the reefs. And this is a vision of the future, perhaps, of coral reefs in a high CO2 world. So there's a very rapid loss as you progress to the seeps in biodiversity and structural complexity, with no reef development at a pH of around 7.8. So we think that's some kind of threshold for reef systems. And there was this amazing paper produced this year in Nature. And it's at One Tree Island, part of the Great Barrier Reef. And what they did is they took a whole reef ecosystem and brought the chemistry back to what it was like in pre-industrial times. So they restored it to pre-industrial conditions. And what they found that the calcification of the reef actually increased by around 7%. And that indicates, it's the first indication, real indication, that ocean acidification is already impairing reef growth. And there are other observations showing decreasing calcification over the last 20 years of reefs in the Great Barrier Reef. Also in the Mediterranean, there are carbon dioxide seeps, but in a different environment. And you can see at pH 8.1, which is today's pH, is amazing biodiversity, lots of calcifiers there again, and then just 0.3 of a change in pH as you move towards the seeps, a great loss, a tipping point to very low biodiversity. But some organisms are doing quite well. You can see some algae doing very well. And the other important ecosystem provider are cold water corals, and they essentially build reef-like structures, but on the skeletons of their past generations. So this is jumble of skeletons, and they produce habitats and nursery grounds for fish. And they may be particularly vulnerable because they actually grow deep in the water where carbon dioxide is higher. And then you actually have more CO2 coming in, which raises this saturation horizon towards the surface. And so we worry whether this horizon will actually move through where the current deep water coral reefs lay. And you can see they're around the European coast, but they're around many, many coasts. And they're also in part important in Northern Europe. And this is the projections for the RCP levels as you move into the future. And you can see the yellow and orange spreading, and this would imply that these organisms and the bones of their ancestors that are forming the reefs will actually dissolve because they've got no tissue to protect them at all. The variability of ocean acidification impacts it relates to the life cycle of organisms in the marine environment. So that organisms that sit on the benthos actually have a well, and this is how they disperse through the seas. And you can see in the lower circle there that the adult of this echinoderm is actually quite okay about ocean acidification, not too vulnerable. But as you move to the gametes, the embryos, and the juveniles, you can see that the vulnerability increases. So you actually have to study the whole life cycle as well as the physiology of these organisms to actually understand their vulnerability to ocean acidification. There's more evidence of the coast of California and in the Southern Ocean that today these pteropods, these sea butterflies, which are the size of a very small lentil, are actually, their shells are corroding as we speak, as I speak. And why are they important? Why should you care about these things? It's because they're very important links in the food web for, from the very small microscopic organisms to the larger things that we like to enjoy and cultivate and catch. So salmon, herring, and whales and many birds depend on these links in the food chain. The ocean is also absorbing nearly all the heat, as Phil said, from global warming. And that is warming the ocean as well. Again, we'll hear more about that later. And that is having an impact in combination with ocean acidification on many marine ecosystems. So what I'd like to do, I don't want to step on the ground of other presenters, is actually look at what the climate scenarios are and the impacts that they have. So these are the changes in mean values, global mean values, since pre-industrial times that will occur by the end of this century. So the present day mean air surface temperature is just over 1. If we go to business as usual, the red line, it will be over 4, or around 4 degrees centigrade. The NDCs, depending which tracker you take, will be anything from 2.7 to 3.5, and the recent UNEP gap report had it at around 3. So this is still very, very high. And the Paris Agreement goal was 1.5, which is very close to the RCP 2.6. So how does this translate into the change in sea surface temperature? Well, today it's already at over 0.8 degrees centigrade as a global mean. And if we continue business as usual, it will be over 3 degrees centigrade higher. If we do implement these NDCs, it will bring it down to between 2 and 2.6 degrees higher. So that's still very high. In terms of acidification, at the moment where the pH of the ocean has decreased by 0.1 of a unit, doesn't sound much, but it's around 30%. And if we keep on going, business as usual, it will be a decrease of 0.4, which is over 120% decrease. And even with the NDCs, they are still quite high, with a decrease of 0.2 to 0.3 pH. The Paris Agreement goal will deliver around a decrease of 0.15. So it's starting to sound better, but how does this translate in terms of impacts on important ecosystems and the goods and services they provide us? This is a planetary boundary diagram, and you'll see that the center is white, which it means that the risk of impact is undetectable, it's very low. The yellow circle is when it moves to moderate, and the red is when it moves to high, and the purple is when it's very, very high. So if we focus on where the blue line is, which is the coral reefs, you can see that the business as usual is that dotted line on the very edge of the purple. So that's very high risk to keep on doing what we're doing. The NDCs move in a little bit, but it's still in the very high risk category. And if we're good citizens of this planet and we achieve the Paris goal of 1.5, you can see that the risk of impact to coral reefs is reduced considerably, but it's still a high risk. And if you look around at the other ones, there are important things like pteropods and krill and other key ecosystems, and then look at the goods and services, you get an idea of how that could impact the marine environment and what we gain from it. So just to close, I conclude that current NDCs are not enough to avoid high risk of impacts to ocean ecosystems and the goods and services they provide. We need to ratchet it up. We need to build on them urgently. So thank you very much. I would like, it's now my pleasure to produce my colleague who is the co-organizer of this event, Dr. Svante Bodin, and the president of the Swedish Meteorological Association, Previously, as he was head of the Division for Climate Change in the Swedish Ministry of the Environment, amongst other very eminent positions. So Svante, you have the floor.
Thank you very much, Carol. I think that was a very good start for this side event. I will pick up where I think Carol left and look at the water on land instead, and frozen water, that is the cryosphere of the Earth. And not unexpectedly, and as we have heard from Phil Duffy here, there are great risks for passing certain thresholds that will lead to irreversible processes melting the cryosphere. I will start right away actually with summarizing what I'm going to say and what the main conclusions are. This is a diagram that looks a little complex. You will have a chance to look at it again. But what it shows is actually how different thresholds are passed and how different irreversible processes are starting for different global mean temperatures. And as you can see, there are parts of the cryosphere that are affected and start their trip towards passing thresholds already at this time, temperatures around 1 degree. And one very notable thing is that scientists have established that part of the West Antarctic ice sheet has actually become unstable and started to empty the ice and melt it into water in the oceans. And that could then lead to, over the next several hundred years, of an increase of the sea level of about 3 to 4 meters. But you could also see mountain glaciers are at risk at around 2 degrees. Arctic sea ice, it's very likely that if you go to 2 degrees or maybe a little beyond, you will have complete loss of summer sea ice. There are even dangerous thresholds ahead. If you go up to 3 degrees and above that, you risk actually to start irreversible processes of melting ice sheets over the East Antarctic, and that's much more water. So this is what we are facing, and this is what we should have in the back of our minds when we speak about the current NDCs. So there are all of those good reasons to stay as low as possible, and the current NDCs are definitely not putting us on the right track. And one of the dangers here, of course, and is implicit in the climate system. The climate system actually provides this polar amplification. And as we have heard, it's very in places 2 to 3 times the global average warming. But I say polar, it actually also applies to, for example, the Himalayas and the glaciers. They're also warming much more rapidly than the global average. And this, of course, is then speeding up the melting and the change processes in the polar region. I think it could be good now to look exactly where we are when analyzing the NDCs, or indices as they were called before. This week, UNEP issued their annual gap report on what is actually needed in order to close the gap to stay on a 2 degrees pathway, and what are the current NDCs leading us. And as you see from this slide, actually, if you include also the conditional INDCs, the best value for what will happen to 2100 is that we stay under 3 degrees. We will be close to 3 degrees essentially. So if you multiply that by 2 or 3, you will see that could lead to something like a 6 to 9 degrees temperature increase in the Arctic, and also considerable increase in Antarctica. So what's happening with the ice sheets? I briefly then mentioned about this instability of West Antarctica, and it has actually been demonstrated that the Amundsen Basin in West Antarctica has already started. It has tipped. So what you can expect from that is an additional 1 meter of global sea level rise, but not on the time scale to 2100, but over several hundreds of years. but the general belief is that this is irreversible. You can only affect it and slow down this irreversible process, but keeping the temperatures down. And of course, this irreversibility is the really threatening aspect of what's happening in the cryosphere. And as I told you before also, the Wilkes Basin in the East Antarctica turns out also to be unstable. And there are many basins that have the same characteristics. And this could lead to 3 to 4 meters of sea level rise. Now speak about other basins in East Antarctica. That has not started yet. It takes a higher temperature to achieve that. And the time scale is much longer, several thousand years. In fact, if you analyze this, you can see that the roots for this are 3 types of instabilities. For the West Antarctic ice sheet, it's referred to as topography downward sloping towards out over warm sea. That is triggering in. So it's not melting from the top, it's actually melting from the bottom by warmer ocean water penetrating in under the ice sheet. When it comes to East Antarctica and the Wilkes Basin, it's actually an ice plug. You have ice that are stuck over land or out of the sea by an underwater ridge that is keeping the ice in place. If it actually melts so that the ice can slide over that ridge, then the whole basin becomes unstable. And you have a third instability, and that applies to Greenland. And that is the high temperature feedback. When it starts melting from the top, the surface of it becomes lower and you get exposed to even higher temperatures. And that you can see have started in Greenland, but not to the extent that the probability yet is so that you can see the whole Greenland ice sheet starting to vanish. But if you look at this probability diagram showing the global average warming over pre-industrial times as compared to the probability of complete loss of the Greenland ice sheet. If you look at the 3 degrees from the GAP report here, there is almost certain, it's more than 80% probability that all of the Greenland ice sheet will vanish. That adds another 6 meters to sea level rise. Permafrost is one other of those irreversible processes. Once the permafrost has thawed and released its methane, it cannot be put back in the ground again over reasonable time periods. 24 of the Northern Hemisphere land area is actually permafrost. And what's happened, of course, is that when temperature rises, the ground thaws, it releases carbon dioxide and methane. Methane, of course, being the very potent part of this carbon stock, and leads to climate warming. But of course, there is also feedback loop, then more warming, more thawing. So if you sum up and they go through a process of calculating how much carbon that could be released this way, we can see in order to stay between the 2 degrees target, we cannot release more than 290 gigaton of carbon. To date, we have then spent about 550 gigaton of that budget, and remaining is 275. Permafrost will add another 130 and 160 gigaton if going above that. So that is a real uphill struggle to prevent that from happening. Arctic sea ice is another, of course, interesting thing and threatening thing. That, however, might not be irreversible. This is only from this year and the latest observation about the sea ice. And what's striking with what's happening now is that even if we didn't reach the summer low of 2012, it's below 2 standard deviations of what's happened over the last 30 years. But the IPCC, and based on a number of Earth system models, came up with this picture showing that for the 8.5 RCP scenario, it's very likely that all of the summer sea ice is vanished around 2050. But on the other hand, if you can stop the warming at 2 degrees, then there is a chance of actually stabilizing the loss and not see all the ice vanishing. But only a couple of days ago, there was a new article in Science that showed that there's a very clear relationship between CO2 versus sea extent. So you have the cumulative CO2 emissions to the right, and you have extent of sea ice on the vertical axis. And so far, since 1953, there is a linear relationship. And if you extrapolate that to no sea ice at all, then you will see that it only takes 1,000 additional gigaton of CO2 emissions to get that. And if you do this calculation, you will see that will lead to about the same time as was predicted for 8.5, about 2050. It might occur earlier, actually, if you get this sort of galloping events that we have now. So I will come back to the picture again. You see that very, very important parts of the cryosphere can pass crucial tipping points and then start irreversible processes. And if you then put in the 3 degrees that we were speaking about before, you see that almost all of these processes will have started and continue actually to deliver their end results. For example, the complete loss of the Greenland sea ice and the sea ice, Greenland ice sheet and the Arctic sea ice. So that was actually my last slide. If you're interested to read a little more about the thresholds and closing windows, there is a report that we published last year where you can see a little more of this. Thank you very much.
Thank you very much, Svante. I have now the pleasure of introducing Lars Otto Reiersen. He's the Executive Secretary for Arctic Monitoring and the Assessment Programme, AMAP, the working group under the Arctic Council responsible for monitoring and assessing levels, trends and effects of pollution and climate change on Arctic ecosystems and humans. And I know he's got another publication assessment on the way, so I'm hoping, Lars Otto, that you will be able to tell us about this.
Thank you. Thank you for inviting me to be here this afternoon or this evening. Just waiting for the first PowerPoint to come up here. We have been working with the Arctic for 25 years. The organization in the Arctic goes back to Gorbachev, who calls for international cooperation to change the Arctic from an area of nuclear submarine into an area of peace and science. And that's what we have been doing for 25 years. The 8 Arctic countries and non-Arctic countries we research in the Arctic are providing scientists and data so we can perform the assessments that I'm going to give you a short introduction to here. So we have scientists to make these thick scientific assessments. They're fully referenced, peer-reviewed. We have a scientist writer to make the layman styles, and that is still too thick for the politicians. So we have this very thin paper with a lot of big pictures and big letters so that we hope that the ministers can read and see our conclusions and recommendations. And nice pictures, as you have seen here, is very important because they look at them and they read the text under. So that's where we try to sneak in the real things. The first PowerPoint should show the area that we are covering, and that is the whole Arctic, north of approximately 60 degrees. So it's a huge water area, the Arctic Ocean, a lot of ice. It's coming. Good, good.
It's worth waiting for.
Just say okay.
I'm just seeing the
just
preview.
click okay. It's just a picture. It's always coming up. There's a picture. There's something. But just say okay.
Move on to the next one.
Click okay.
We will when we get there.
Oh.
We will skip the first slide. You're suggesting to skip the first slide, are you?
Yeah, that's okay. If the first slide is...
Is that what you're saying?
No, just say okay. No, it's okay. Thank you.
Okay.
There we are. That's the area. You see, it's quite a big area we are looking into here. And we are looking into the ocean, the land, the atmosphere, and the humans, analyzing the levels of contaminants. I also see on the effects here. And let's see. This is the report on the cryosphere. This is the third climate report that AMAP delivered in 2011. And in April, we're going to launch the next report telling the development of what we see now in the cryosphere in the Arctic. And then it will go 2 weeks later to be presented to the Arctic Ministerial Conference that will be held in Fairbanks in 11th of May. So if you're interested to learn more, Washington in April is the place to learn this. This is the model Jim Overlands have used for the work I've been doing here. This here is from the Northern Hemisphere, RCP 4.5 and 8.5. But if you look at what's happening north of the 60 degrees, you see that we have more than a doubling in the temperature. If you continue as business as usual, the red line, in the winter time, you will be an average increase of 12 degrees. This illustrates how important it is to look into areas, into part of the year, and don't be blind on the average of the globe. That is what you see here. That is 5 to 6 degrees. Or don't. In the Arctic, you see doubling, and be aware of that in some areas, some part of the year, you will have extremes higher and lower. And that's important to understand what you then get for the melting of the ice, the thawing of the permafrost. The average is not the right to look at. You have to look at what's at the site, what will happen. So this is also an interesting thing. We have heard it before. The ocean has been under-communicated, the heat of the oceans. This is inflow of warm water around Barrow in Alaska coming into the Arctic. This is in September 2011. Interesting too, the input of warm heat by the rivers. Some of the largest rivers in the world are emptying into the Arctic, and that's another heat pump into the area, contributing to the melting of the ice and then reducing the freezing of the ice in the autumn, which is one of the reasons why we have some extreme weathers. I will come back to that. So this is what we have seen is the thawing, this melting of the ice. If you're going back to the old days in the 80s, a lot of multi-year ice, more than 6 years old, 6 meters and bigger, dominated. Today, hardly multi-year ice. It's 1 to 2 years ice dominating in this area. What is under-communicated to the world is the snow cover and the change in the snow cover. And again, we see here in June, we see up to 50% reduction in snow cover in a huge part of the Arctic. And then we see that is continuing. This is from 2012. Thawing of the permafrost, you heard about that. What is interesting is to see there's a difference here in the thawing of the more warmer part, the discontinuous permafrost area. There's not that deep, steep increase in the temperature. But look what's up in the upper figure here. In the continuous permafrost, there's an increase in the temperature of 2.5, 3 degrees. You should be aware of the thawing ongoing today is the permafrost created during the little ice age. The permafrost creating from the last ice age will start thawing in mid-century if you don't stop it. So this is still rather new permafrost that is thawing for the moment. So what we see what's coming up in the Arctic will be much more wetter. There will be increased precipitation and increased evaporations. And that means that you get a hell of water out of the Arctic, not only from the melting of the ice, but also from the weather conditions. This is from a flooding in 2015 and the Dalton Highway. And you will see much more of this in the future. So coming back to where we had the Arctic, when I grew up in Tromsø and what people had, we had this situation in the upper left here. The cold air started in the autumn, spreading down over North America, Europe, like a dome of cold water air. And it stood there into the spring and came back again, picking up pollutants into the atmosphere. And then you saw this beautiful color called Arctic haze in the late 50s because of these accumulations from Siberia, from Europe in that area. What happened in 2009 and 2010 was the break. You got this heating in the central part of the Arctic, and you get the outlet of cold air, just like you have today, coming down all the way down to Spain. You have the warm here and then cold. And we have just the same situations going on now. This is an average air temperature increase in the area from the last 15 years compared to the previous 30 years. And you can clearly see here the increase of the heat, mainly over the oceans, between Greenland and Baffin Island. That's where we have the huge increase in temperature in the Arctic. And of course, that is part of the reason for why we have the increasing melt of the sea, of the land, in addition to the heat in the ocean. So then we have the situation that the empire strikes back again, like I called it. People see now the feedback from the Arctic, the extreme weather, snowing in Washington in May, heavy rain in England a few years ago, fires, forest fires in northern Norway. It was absolutely crazy period a few years ago. And what we see here is this jet streams affecting southern parts, and we also see effects correlated to the monsoon in Southeast Asia is correlated to the ice conditions in the Arctic. And lots of several publications are out on that part. The Greenland ice sheet was more or less stable until the mid-90s. These are observations. This is in the previous release from AMAP. What was snowing on the top of Greenland, exactly the same, more or less running off. Then you can see how it started to increase. So when we released the sweeper report in 2011, the runoff of Greenland was approximately 250 gigaton of water. What on earth is that? Well, that is 1 meter of water all over Australia. So this is increasing and continuing, and other glaciers, ice caps in the Arctic are melting. So the Arctic is today one of the main contributor to sea level rise, together with the temperature expansion of molecules, and that will continue. AMAP presented, the sea level rise estimate in 2011 was between 0.9 and 1.6 meter. Hardly anyone believed that figure when it came out because IPCC had just released and said 0.3 meter. But we had the new figures then from Greenland and from Antarctica. And we will see then when they are coming with the new figures, they are around a meter and above. And it's again, a sea level runoff from the Arctic will affect southern oceans. So the increase in the Indian Ocean will be 1.6 higher than the average. And again, don't be blind on the average figures. Look at the reality there and then. This is, yeah, and just one funny thing for many people. When Greenland is melting, Greenland will not have a sea level rise. Greenland will have sea level decrease because ice melting, the weight on Greenland is lower, and Greenland will come up. Black carbon, you had heard that already. Sources around the Arctic of black carbon emissions. Just want to point on this one. The main source in the Arctic is the emissions from oil fields, the flaring, and there you can see there's some, it's hard to see here, but the big red to the far right is around the Russian sites. But the main source of heating of black carbon in the Arctic is the black carbon in Southeast Asia because of the heating in the atmosphere and the transport of the heat into the Arctic. So what we need is we want actions on black carbon. We need global actions on black carbon and methane if you want to have the effects of a reduction of the temperature of up to 0.5 degrees by mid-century. Actions just in the Arctic will hardly have any effects. Ocean acidification, Arctic is going more faster than most of other areas to be acidic because cold water can store more CO2 than warm water. And when the ice is melting, you get more fresh water in. And when the ice is melting, you get more surface area available to absorb CO2. And then you have this huge amount of carbon coming out of the Russian rivers. All of this is making the oceans more vulnerable. The Arctic marine ecosystems are likely to undergo significant changes. And we are now doing a new study that we will report of what are the effects on the socioeconomic, on the fisheries. And this is a figure from the first assessment we had, Arctic Climate Impact Assessment, where one predicted that mackerel will move north. When I grew up here in this area, we didn't see mackerel. It was up here. In 2007, mackerel was here, and last year mackerel was up here. So we see these predictions from ACCI is taking place. You can fish mackerel far, far north. And then it is, what are the effects of ocean acidification and temperature and other stressors? That's what you're looking into now in case studies around the Norwegian coast, in Alaska, in Baffin Bay area, to see what this means for the fisheries and for the local indigenous people, for their living conditions in the Arctic, and what they can export of fish from the Arctic. So this is a very interesting study that will be released. The first report will be in May next year. So how to adapt? It is not enough to mitigate. we have to start to adapt and plan the adaptation. So that's what we are doing this. What are the combined effects of all the stressors in the Arctic? We have chosen 3 regions looking into here, and they're looking for how can we prepare the local societies, the business, to prepare for a future that is totally different from what you have today. And that will also be released. And this is just to illustrate from the Chukchi Sea. This is today. Normally you have ice in this area 11, 12 months. And then you can see what the models predict, that when you're coming into around mid-century 30, 40, you have 2 to 3 months, shift from 2 to 3 months to 4 to 5 months without ice. Dramatic changes. And that will also have effects on the sea that is protecting the land from erosion. We saw a nice picture earlier. So some of the conclusions we can draw is that the Arctic temperature will continue to increase, both in the atmosphere and in the ocean, and thereby an increased volume of meltwater will come out of the Arctic and affect the global sea level. If Paris Agreement is achieved, that was trying to achieve 2 degrees or 1.5. Unfortunately, that will not be enough to stop the melt, but it may reduce the increase. The increase in 2 degrees, as I showed you, means 4 to 5 degrees in the Arctic, and that's a hell of water. Arctic will be different, the world will be different with what's happening in the Arctic. And into this, ocean acidification will continue and have effects both on the chemistry and the biology and the socioeconomy. So all of these new data you will listen to. You're welcome to Virginia next year. Thank you.
Thank you very much, Otto. That's quite depressing, really, isn't it? We will have questions later. It's my pleasure to invite Professor Hans Otto Pörtner. Hans is an eminent marine physiologist. He works at the Alpha Vega Institute. And this year he took on the challenge of the IPCC co-chair of Working Group 2 for AR6 and the Ocean and Cryosphere report. So Hans, you have the floor. Thank you.
Thanks very much, Carol, for the introduction, and thanks a lot for the opportunity to be here and talk to you about the activities of IPCC in the context of oceans and cryosphere. There will be 3 reports that are in the pipeline that have been initiated during the government plenary in Nairobi earlier this year. And the IPCC has started the process. There will be a special report in 2018 on global warming of 1.5 degrees, where the outline has been approved by the IPCC plenary just 2 or 3 weeks ago in Bangkok. And there is a special report then also underway to be finished in 2019, climate change in the oceans and the cryosphere, which will be scoped in Monaco in early December. And certainly we do not have any indication on content for that, but some of the colleagues in the room will be present at the scoping and work with us on the outline. And then there is a main assessment and synthesis report that needs to be prepared, which will actually be scoped already in May of next year, but will only be finished in 2022, including ocean, coastal, and regional assessment. So as an indication of what the outline looks like for any of, or can look like for any of these reports, I'm showing you the outline for the 1.5 report, which, based on the fact that we are now have 3 special reports that are underway. I should mention the land use, desertification, and so forth special report, which does not consider the oceans. These special reports will be quite short, in this case up to 225 pages. There will be a summary for policymakers, and there will be 5 chapters. One on framing and context, the next one on the mitigation pathways possibly leading us to 1.5 in the context of sustainable development. There will be one major chapter on impacts, which has to cover all systems, natural and human systems. This will be the largest chapter. And then there will be a consideration on how to strengthen and implementing the global response to the threat of climate change. Then we will consider sustainable development, poverty eradication, and reducing inequalities. In such a short report, the regional and examples and those examples which show a high sensitivity or maybe even successful implementation of adaptation and mitigation measures, they will then be scattered across the report. Let's have a look at chapter 3. That's how the outline develops. It's usually under each chapter heading. You have a set of bullet points where you go across what should be covered in the report as a recommendation to authors, but certainly not constraining authors in the possibilities of their writing. So there are the methods of assessment, and then the observed and attributable global and regional climate changes and impacts, as well as the adaptation experience. And then we look at key vulnerabilities, impacts, and risks at 1.5, also looking at socioeconomic aspects and comparing these and to the avoided impacts and reduced risks. So it should be a comparative treatment of a climate world in 1.5, because comparison is needed to put this into perspective. Time frame will be an issue, and mitigation pathways. This is just an example of what should be treated in that report. And some of this may already building on the AR5, where there has been consideration of vulnerable ecosystems, and there has already been information which allows us, mainly with the RCP 2.6 scenario, to draw on information for 1.5 degree warmer world, as you can see here, where according to IPCC findings, we can make the distinction that in a 1.5 degree warmer world, there may be sea ice left, some in the summer in the northern hemisphere, whereas in a warmer than 2 degree world, we are looking at a situation where the sea ice will be completely lost. And you've seen this figure already, where you see indicated how in a 1.5 degree world, the situation may stabilize with some residual Arctic summer sea ice left, but you also see there is quite a range of uncertainty around that needs to be considered. Now, what else can we say about the world under different degrees of climate change? This is looking at the oceans from the point of view of productivity shifts, and these are latitudinal shifts that concern virtually all organisms, but also those that represent primary production. And you see how in a warmer world, productivity is moving north, moving and south, moving to higher latitudes. And this trend is exacerbated in a business as usual scenario. And you see how the so-called desertification of the ocean gyres at mid-latitudes is actually exacerbated by a warming ocean. This also reaches up to the higher organisms, where again, organisms move in response to the warming trend. You see the reddish areas here, where there is a decline in biodiversity and decline in fish stocks and invertebrate stocks. This summarizes information for about 1,000 species, where we see a decline in fisheries catch potential at low latitudes, affecting especially the developing countries and their artisanal fisheries in those areas, whereas in some higher latitudes, you actually see the blue indicating an increase in fish stocks. But on average, there will be smaller fish, and there will be about a 20 to 30% decline in fisheries catch potential in a 2 degrees warmer world. And these trends, as far as we know from a recent projection exercise, are exacerbated by the warming-induced oxygen loss from the oceans. Now, what else is happening, indicating a transition of critical thresholds? And there's one system where we all know that it is already affected by the warming trend, and these are the warm water coral reefs. You see the shift here from a healthy coral to a coral that has, to the left, to a coral in the center that has lost all the energy producers, the algae, that they cannot keep inside anymore in warm temperatures. They could recollect them during short periods of exposure or after short periods of exposure, but if the heat waves lasting too long, the reef will essentially turn into a desert, as you see on the right-hand side. And in fact, for various reasons, not just for the reason of coral bleaching, the Great Barrier Reef, as an example, has already lost 50% of its live coral cover since the 80s. This trend is continuing, and even in a 1.5-degree warmer world, we already see a high risk of losing up to 90% of coral reefs and their services to humankind. Ocean acidification has also been mentioned. You see the different trends here in the inset, where the pH decline, which is measuring, quantifying the acidity decline, will either go unabated in a business as usual scenario, or with ambitious emission reduction will be reduced. And you see the different calcifiers here in the acidified world, indicated by the bluish colors according to the pH scale. You see again the trend of high acidification in high latitudes, especially in the Arctic, because there's also freshening happening. And then you see the ecosystems affected, the warm water corals here, the green dots, the purple dots indicating the cold water corals, and then the yellow areas indicate the areas where humankind relies on calcifiers for fisheries. We know that sensitivities differ between different groups according to the different CO2 exposure experiments that have been done, and which can serve kind of projections of how these groups will change in the future. And you see that the fraction of sensitive species early on is high in the mollusks, is lower in the crustaceans, and is high again in the corals, but lower in the cold water corals than in the warm water corals. This gives us some projection for acidification impacts by the end of the century. And we know again that risks are enhanced by warming extremes. Now, how do we bring all of this together? You have already heard Carol talking about the assessment of risk, and actually the risk concept developed by Working Group 2 during the last assessment cycle has been a role model for this. And you see here the burning ember diagram, which distinguishes the risk from undetectable to very high according to color code, and how we can then allocate risks according to the different long-term global goals that are being discussed. And the natural systems actually play an important role in terms of developing that risk, developing a picture for those risks and the resulting long-term climate targets that we should go for. Well, you've seen this slide already, and actually we've been bringing the IPCC model of risk assessment together in this paper, actually this year in Nature Climate Change, where you see the sort of planetary boundaries for the oceans associated with the temperature, different temperature worlds. The black line gives the 0.8-degree world, and the white line, the 1.5-degree world. All of this is in the yellow area, moderate risk area, except for the coral reefs, as Carol has indicated. And we can pretty much confirm and emphasize here that all of the INDCs, which would take us to a 2.7 or 3.5-degree warmer world, would take us into a high risk in a situation, and which should initiate and increase then the ambition for further mitigation efforts. A final point, sea level rise to be addressed has already been discussed widely, so I may be able to cut that a little bit short, just to say that in the last synthesis report, actually, we were assuming that in a 1.5-degree world, there could be sea level could be constrained to below 1 meter. But as already said, the contribution of the Antarctic ice sheet is likely underestimated. This makes an important distinction, and a recent paper by Strauss and al. Actually distinguishes the triggering of the ice sheet for the different scenarios, and you see different levels of exposure to sea level rise here according to these scenarios where different areas are more strongly exposed and certainly with increasing warming trends. There's a large uncertainty with respect to sea level rise. Even in a 1.5 degree world, we are not really firm about which level of sea level rise we will actually be reaching. But with this kind of consideration, we are coming close to situations from paleo findings, which have been compared to the present developments, where similar levels of high sea level rise have been reached. So there are high risk thresholds that we are about to transgress, and we need to say, certainly we need to take action. Adaptation is one action, is necessary and is occurring, but without ambitious mitigation, adaptation will not be sufficient. And this slide, which may actually, during this week, especially the left-hand side, may show how important this consideration actually is, that there is a science background in human behavior that needs to be considered when we discuss the societal inertia and the inaction in transformation. As part of this process, we need to strengthen the visibility of the ocean by its formal integration into the UNFCCC process. And as part of that, we need to enhance and exploit the science basis of ocean-related solution options, like setting up of marine protected areas, identify limits to adaptation, consider blue growth and sustainable development for these economies. And with that, I would like to close and thank you very much for your attention.
Thank you very much, Hans. I think the urgency of ratcheting up our CO2 emissions has come across very strongly indeed. It's my pleasure to invite Vladimir Ryabinin. He's an oceanographer, a climatologist, a marine engineer, and at present serves as the Executive Secretary of the Intergovernmental Oceanographic Commission of UNESCO. Vladimir, you've got 12 minutes.
Thank you very much, Carol. You know, actually, you see what's happening with the planet Earth, and I'm standing between, well, the talks and the dinner. It's a very difficult situation. So, in principle, what I would like to state that I wish to take us from the last picture that Hans Onte shown with heads in the sand. So we need to do something about this. And, you know, at least the IOC of UNESCO will try to do something when it comes to the ocean. But the distribution of mandates is pretty complicated in this world. So, you know, I would like to also discuss with you some multidisciplinarity in the Earth system. Lars Otto already said that, you know, that if Greenland ice sheet melts and the Antarctic, then sea level rise will be mostly in the tropical areas. But this is what we see now. This is the current picture of highly uneven sea level rise. It's affecting mostly maritime continent, and then let us look where the strongest tropical cyclones are. And we still remember that cyclone Hainan that destroyed a lot of villages in Philippines. But you know, this is kind of environmental look at the problem. But if you look at what's happening in these big cities, they kind of tend to develop exactly in this region. And of course, people tend to go towards the coast and they live on the coast. But what is important also, these mega cities, they're so heavy, they extract so much groundwater, they tend to also subside. And the speed of this subsidence is even higher than the speed of sea level rise. So we not only have these environmental problems, but a lot of engineering problems and civil protection problems that all need to be considered together. If it also consider on top of that, that this is the area where we are losing a lot of mangroves, which also contributes to increased carbon in the atmosphere, then we see there will be some really hot spots on the planet that we can shoot and have to react on. So what can be done? In principle, and already Hans Otto spoke about this, the CMIP experiments and also Lars Otto used these experiments are highly influential and highly informational because, you know, they are done with the Earth system models, including the coupled ocean atmosphere that driven most of them by emissions of greenhouse gases. And they are able to provide with good guidance on the physical part of the climate system, also on chemical part of the climate system. With that, it is possible to at least see what is going to happen with large marine ecosystems. So this is a very good instrument for driving management. But of course, on top of that, we have highly developing, fast developing observing system in the ocean, particularly also when it comes to physical domain, much less when it comes to biological and biochemical and ecosystem domain. But we are also going in that direction. Observations are incredibly important for understanding what is happening, for driving science, and enabling the models as well, because they have to be tuned using best observations. So with that, it is possible, I think, to use the CMIP experiments that produce so-called IPCC climate projections and predictions for at least mitigation scenarios for managing the ocean better. Now, of course, the perspective is that we will turn this into truly Earth system models that also include economics, include regions, include industry. This is where the current science is going, but we are not yet there. But at the same time, we need to imagine that with this type of science, there'll be more transparency in the world, more ability to check what is going to be according to certain decisions. This will be, I think, in the future, the mainstream development of Earth system science. Now, so there are different communities that are dealing with. Of course, there are scientists, just general people, governments, private sector. I am presenting here facilitators or enablers. They may come from non-governmental organization. In my case, this is an intergovernmental organization, the Intergovernmental Oceanographic Commission of UNESCO. So what we actually can observe in terms of this zoo of different acronyms of different agencies and different groups involved in ocean governance. So this is that value chain that comes from ocean research, then goes through ocean observations, generates certain data, and this data are used in two modes. In real-time mode, they're used for providing certain services, meteorological, for example, predictions, and of course, they also used in delayed time mode for producing different certain assessments, like an IPCC assessment, like Hans Otto was presenting. And of course, this comes societal benefit. If we then click again, we will see how this diagram is populated with different groups, projects, and programs. So we are actually nearly everywhere, the Intergovernmental Oceanographic Commission. We are sponsoring some organizations. We are contributing to the work of some of them. We are communicating with others. So one of our staff produced that picture, Kirsten Easensee, of a lot of projects that we involved with, including Global Ocean Observing System, including the World Climate Research Program, the Blue Carbon Initiative. So we are basically a governmental think tank that produces some initiatives that are most important for governing the ocean, for understanding what is happening, and I hope very much that this is useful also for decision making. And then indeed is really driving certain processes. But we already have some frameworks that may help us to process scientifically based information and come to good decisions. So these processes are reflected in certain frameworks. Of course, we should start with the Agenda of Sustainable Development, Agenda 2030. We have now the historic climate agreement achieved in Paris. We have also accelerated modalities of action for small island developing states that are very strongly affected by climate change. We have also the new Sendai framework for disaster risk reduction post-2015, and there is a constitution for the oceanographers, United Nations Convention on the Law of the Sea. So we try to use all these mechanisms and try to use the constitution to move forward on certain decisions. So what is happening, for example, in terms of governance? More than 50% of ocean surface is beyond natural jurisdiction. If countries would like to protect their biodiversity in the exclusive economic zones, then this area remains unprotected. So now there is a decision that there must be some legally binding instrument for protection of biodiversity beyond areas of natural jurisdiction. This process needs to be informed. So we work with United Nations in New York, and we conduct the certain events like here, and we inform them that we need to derive that regime, and very likely this regime will be, I think, designed and agreed, I would say, in 2-3 years' time. Now, there are also already specific things that we are responsible for, and some of them are reflected in Sustainable Development Goal 14, the standalone goal on the ocean. So this goal includes actually 10 targets, and they are related to elimination of pollution, turning fisheries into more healthy mode in different ways, particularly by removing substitutes to huge fishing fleets that basically have huge bycatch, and they also basically kill fish nearly everywhere. So we need to also increase the area that is protected in the ocean, and we have to do it well, less politically less political, but more kind of science-based. But IOC is responsible for two very important things there. We need to engage the community into studies of ocean acidification and trying to find ways of dealing with this. So a lot of people in this room actually contributing to this very important process. And the second thing that we are responsible is the target for 14A, a cross-cutting target. We need to build the capacity of ocean science and transforming technology. It's not technology is not really kind of instrumentation. Technology is information technology, databases, the ability to process data, include models, take results from the models. So we try to do this, and we actually one of those organizations that explicitly mentioned in all these targets that our criteria are going to be used for that process. This is really important to move science forward, to address cutting edge requirements of science, at the same time creating such conditions that developing countries can benefit from the science and contribute to its move forward. So now, what needs to be done in the ocean? And Hans already started this topic. We need to improve, still improve integrated coastal zone management. We need to, again, improve maritime special planning. We need have a new regime beyond areas of natural jurisdiction. We need to have scientifically based marine protected areas, increase the surface of these areas, and enforce that these areas shouldn't be touched. There are some means of do so. And of course, we need adaptation and mitigation. Everyone understands we really need this probably the most to save the planet from increased CO2. What are the ways of doing so? We need to engage the potential of private sector. Blue economy is probably the most promising economy and very stable. So we need to engage that sector also in adaptation and mitigation. And of course, we need to create literacy in people, in kids, so they know what to expect into the future. So once again, for that, we need to increase the capacity, and we are actually measuring capacity. For the first time in history of ocean science, we are going to issue a report that measures the capacity of science, infrastructure, investment, interest, gender balance, topics. So this is the substance of the Global Ocean Science Report that we unveiled at the Sustainable Development Conference of Sustainable Development for the Ocean in June 2017 in New York. And we have to develop the network of knowledge. For that, we need policies. We have open data policy. We create networks of scientists, of knowledge, of best practices, of data information. We also create technical means of dealing with that. So what is also important that we have some guidelines on transforming technology that are developed by IOC, and with that we hope to help developing countries to be really key players in this process. And this is my concluding slide. You know, I think several years ago, and I think it was particularly true in 2009, when all the science was already there, but the COP in Copenhagen didn't agree on anything. So then scientists started to think, what is the problem? So how we communicate our science? And the model that was used till that time was kind of linear. Science was the truth. Truth would speak to power, to governments, and governments were supposed to listen and take actions. This didn't happen. So now there is a much better understanding of that the process should be not really linear, bottom up. The process should be kind of much more complicated. Scientists should really act as owners, brokers of that information. There is some responsibility attached to knowledge. Lars Otto, Hans Otto, everyone here spoke, and we know more or less with certain uncertainty that what is going to happen. We need to communicate this. If we don't do this, the world will be in big trouble. So this is the model. This model is not non-linear, and I think this co-design with governments is the way forward. So we speak to governments speak to us, then there is a common understanding achieved. This is how we probably can move forward, also in the climate domain, in ocean protection domain. And you know, this is much more than that. Lars Soto presented to you the dramatic situation in the Arctic. But you didn't say that even the ozone hole was emerged during several years. So such things may also happen. So the world is really complicated, multidisciplinary, and we have to have mechanisms to address this complexity. Thank you.
Thank you very much, Vladimir. Another bucket of cold water. Okay, I'm handing over to Svante to do the questions.
Fine, thank you very much, and thank you very much to all the speakers here. But we don't have such a long time left, actually, only 10 minutes of the allotted time. So I think it would be useful not only to allow one question per person. So I see immediately someone raising her hand, so please.
Thank you. Thank you for our distinguished panelists for the great presentation. I think science has spoken for a long time and has stated truths and facts for what they are. Now, Carol mentioned that the national contribution, intended contribution of countries are not enough. I would like an elaboration by the panelists on this question. What is the right national contribution, the intended national contributions that should keep us away from higher rise in temperatures and acidification and, you know, other ripple effect of climate change?
Who would like to start? That's a very generic but very important question, actually. Yes.
Thank you.
Yes.
Thank you, Svante. Actually, there is no alternative, of course, towards tightening the contributions. But you know, I just wanted to comment on something that hasn't been touched here. The order of events in the Earth system is very important. If you release all the carbon almost immediately, then you will engage a lot of natural feedbacks in the system, and it will be much more difficult to have. You will have much higher negative emissions to compensate for this. So everything that is possible to do now in terms of blue growth, in terms of using blue carbon, every contribution that we can do now will probably pay off if we can just make it. So we have to start now. And protruding on this, it takes us into a more risky world. That's the only thing I know. The rest is for countries, for contributions.
But I also think that IPCC has demonstrated very clearly what is required in terms of emission reductions in order to achieve both a 2 degrees goal and 1.5 degrees goal. And now we get further information on the 1.5. But I think how that emission reduction, of course, is turned into INDCs or NDCs, then that is what this negotiating process is. But they have to sum up to what is required according to following at least a 2 degrees pathway. That's my own personal reflection on this. Anyone else who would like to address that question before we go on to the next one? Yes?
Sure, just
Phil,
to add a point on the question of INDCs. If you look closely at the most recent IPCC assessment report and other subsequent publications, you'll see that the scenarios there that limit warming to 2 degrees, and certainly the scenarios that limit warming to 1.5 degrees, involve not only very rapid reductions in emissions of greenhouse gases, but also carbon dioxide removal, the actual removal of large quantities of CO2 from the atmosphere. And frankly, I think this is something that needs to be much more highlighted. I think it should have been much more highlighted in the recent IPCC assessment report. And part of the reason I mention that is that, in my opinion anyway, the amounts of carbon dioxide removal that are invoked in these scenarios are something we simply don't have the know-how, the means to do. I frankly think it borders on science fiction.
Okay, I think we move on. Oh, you would like to comment also? Yes, Karen?
First of all, I negotiated 5 minutes extra with
Oh, you
the
have, okay.
technicians because we
That
were
sounds
late
very nice.
starting.
Yes, yes. Thank you.
I popped into a economics side event, and they were discussing NDCs and the cost of implementing them. And my take-home message from that was that it is expensive, but it's more expensive, it's more costly to put it off. The cost of not doing anything. So the longer we put off reducing the emissions, the greater the expense will be. But of course, that's the expense of actually reducing CO2 by various means. But the expense, the ecosystem expense of not doing anything is going to be huge. That will come a little bit further down the line. So we need to invest now to save an awful lot of money later, and not just money.
Okay, I think we move on to the next question. Yes, the gentleman here in the middle. He was first.
Mike Kaufman, Planet Hydrogen, Manchester. Could I just say thank you to Philip Duffy for mentioning something which should have occurred in all our discussions, which is a reduction not only in emissions. We are prisoners of the UNFCCC in talking about emissions and temperatures as criteria. We should really be talking about concentrations, difficult though it is. It's concentrations at that level going up and up the whole time, which are the root cause of all our troubles. And we should be taking more seriously, not what is called negative emissions, which is a business-friendly way of using carbon from plant life to make fuels. We should be talking about the physical and chemical and phytoplankton, perhaps, removal of carbon dioxide and its sequestration for quickly, so we're bringing concentrations down to the safe level, which we all know is 280 parts per million. So thank you, Philip.
Thank you very much. Next question. Yes, the lady there with the camera.
Hello, Judy. Hello, Judy.
Yeah, it's on.
Hello, Judy. So it's Mother Channel Television on the internet. And I filmed a fish crime conference last year. And the same conclusion we came to was more or less got along the lines where Vladimir was going with what he was saying now. And it put an idea into the conference's head that there was so much area beyond the boundaries of the seas, the seas that belong to countries, that is sort of like open season to all the worst ruffians on the planet. And there were so many terrible crimes happening out at sea, not only on the fishing level, but also on many other levels as well too. And that there was no jurisdiction of what happened there because nobody knew which area particularly. If you just see sea, you've got no proof of anything happening. And I love the idea that you put forward, Vladimir, and I want to know how you would think of getting this started. You know, we need a world that is ruled by reason. We don't want a world anymore that's ruled by clowns or vested interest. And the vested interest problem is the thing that's killing everything. And how would we put forward an idea where the scientists, the people who represent at least the top information that's coming in at the time for all the different facets of reality that we all deal with, should be the ones who lead the way. We've got the wrong leaders. How would we get the sea becomes a maritime country, one country, because it has no boundaries, no borders, and become where you guys are the ones who dictate what happens there, and everybody participates. Again, I love that idea where everybody, but you know, it's something that belongs to everybody, where there is no overriding one country running everything.
Thank you. I didn't really hear any concrete question. Or
Okay,
how would you start something off?
Okay.
It's something very drastic, but this is the time for drastic stuff.
Okay.
You know, the ice is getting thinner, and I feel that I'm on that ice at the moment. So, in principle, I would like to state that indeed a lot is about education and generating values in young people. I think we are all doomed, but the young people should be getting that education and values that will help them to survive and save the world. But indeed, scientists should speak up, and if they know what is going to happen, it is their duty. And I stay for that. But I think it's just much, much more than that. More than convention on climate change, we need the convention to reduce the greed of people.
Yeah, I think that there is a general consensus about that, but Carol would like to take that a little further.
I mean, I'm really sad when I look at a number of politicians who aren't scientists. We really need more politicians who actually understand science, as well as scientists that can communicate to politicians. So we really need to join this up.
Thank you. And Lars Otto, please.
Just a small comment. All of you have spent a lot of energy to produce readable reports from the science. Looking back, we have maybe addressed the wrong audience, because we have tried to address the decision makers. But it's not the decision makers who vote the politicians. So we have to address the voters, those who elect the politicians, much better than we have done. That's a big failure, the way we have communicated over the last 3 decades.
Okay. Those are very important words, I think. Yes, please.
Oh, thank you. I'm Simon Donner. I'm a scientist from the University of British Columbia in Canada. And I guess my question is following up on a comment that Philip Duffy made about the negative emissions embedded in IPCC scenarios. I guess we're talking about 2.6, RCV 2.6, I suppose. So I'm wondering, and something I think about a lot, is it given the low likelihood of avoiding 1.5 degrees or potentially even 2 degrees of warming, we are looking at quite likely passing some of the thresholds that are being discussed. And so then what becomes the role of the science community, all team of scientists up here, in helping the world deal with the fact that we're likely to pass these thresholds?
Yes. Yes.
Yeah, thank you for this question. This question is being asked very often, because there's certainly a likelihood that we will miss the 1.5. But still, the world wants to know where we stand with respect to impacts and with respect to avoided impacts. And we need a reference for that. And it's then good to have a reference what a 1.5 world would look like compared to a 2-degree world, and compared to a world that becomes even warmer according to present INDCs. So in that respect, such a comparative treatment is important, and then the world can decide which climate target they would like to go for, and which climate target they would think is feasible and worth the effort.
May I make a follow-up question myself concerning that? I understand that you could also consider some sort of overshoot scenarios where you actually go temporarily above 1.5, and then by negative emissions you could come back from above to 1.5 degrees.
Yeah, just to say that this is actually considered in the 1.5 report as well. And this is posing interesting questions for the oceans, because the oceans are a buffer for the climate system. They take up more than 90% of the heat presently, and they're lagging behind with respect to the warming trend. Then you would have to ask, for example, with respect to ocean ecosystems, how much of an overshoot is tolerable with respect to avoiding severe and dangerous impact.
Yes.
Yes,
next question.
If I could add a comment on overshoot.
Sorry.
I don't like overshoot scenarios, and I don't like them for policy or psychological reasons and scientific reasons. Policy and psychological reasons, I don't like offering the temptation of saying, well, okay, we can postpone action now and we'll fix it later by means that we have yet to invent. I think that's a very risky a very risky way to run a planet. The other point which has been made earlier is that certain consequences, certain consequences are irreversible. In an overshoot scenario, you're going to allow more emissions of greenhouse gases, for example, from thawing permafrost. You're going to allow more sea level rise. Those consequences are irreversible. Even if you succeed in magically sucking CO2 out of the atmosphere and putting it somewhere, that methane that came out of the permafrost isn't going to go back into the permafrost, and the sea level isn't going to recede downward. So you have to consider the irreversibility of certain processes.
There's another question also. So could we turn to you? Yes, please. Oh, you have the microphone. You wanted to pose a question? Yes, please. And then you have it.
Okay, I first of all want to thank all the panel for these very interesting presentations. You were just talking about the permafrost. I was wondering if in paleoclimatic data, we already observed such a methane release from the permafrost, maybe at the end of last glacial maximum. I don't know if such a release already happened.
Who would be best suited to answer that question? So, somewhat technical. There are methane releases observed. Yes, but Phil, you might want to address that question.
Well, if someone really knows the answer, I'll
Lars, the
No,
sweeper.
I don't have it, the paleo studies on that. We released a methane report last year, and we were more looking into the future. And we don't see the big explosion that someone had a theory on. What we see is the release of methane will increase as the temperature increase and the thawing. So there will be more or less a linear increase in the release into the future, the decades, and into 2100. So we don't see this big bang that someone had in the newspapers last year.
Okay, one final question then we have to close.
Christian Breyer at Lappeenranta University of Technology in Finland. It's mainly a comment, but of course also indirect question to all of you, so maybe I get some response. When I see and follow over all the years what is done by IPCC, and I want to continue what have been the questions of the two questions before with negative emissions, I'm extremely worried how poor is the understanding of the energy system, which is the main contributor of the CO2 emissions. Because what I saw over all the years, and I have to introduce, I'm researching 100% renewable energy systems in a high spatial and temporal resolution. And I'm really worried how low is the understanding of the energy system in the IPCC reports. It's extremely conservative. The assumptions are conservative. The solutions are thought in nuclear. They are thought in CCS, but we know CCS is a PowerPoint technology. It does not work in the real world. It's used in the oil and gas industry to get more oil and gas out, but not for what we're discussing it here. And when it comes to the renewables, the understanding is extremely poor. When you see even the scientific publications of the last 2-3 years, the cost assumptions for solar PV for mid of this century are higher than what we have today, for example, in India. And we're not talking on batteries and other things. It's just not happening there. So a place I can only call or cry out, discuss with your colleagues that this stuff is done better. Even Hans-Joachim Schellenhuber and Stefan Rahmstorff wrote a Nature climate change comment mid of this year that we cannot continue with that in the IPCC. Maybe you can comment a bit on this.
Yeah, but I guess what you are saying is that really to get some more ambitious NDCs, you need more understanding of what the energy system really is doing. Yeah, I wonder if there is anyone who would like to comment that, or don't we all agree that we need that better understanding of the energy system? Yes. I think that that will be the last sort of conclusion we come here to tonight. So I would like to once again thank all the speakers, but I would also like to thank you, the audience. It's been a wonderful time together, I think. So thank you very much.
is a dinner meeting.
Thank you. Have you got your computer there? No, it's not on there. Have you got your computer here? Okay. Then I can give it to you. It's not on there. Yeah. Could you open it up? Can you go on to this?